Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, we discuss 3 simple steps to understand spectral clustering and how to implement it in Python using data science libraries such as NumPy, SciPy, and scikit-learn. If you find any value out of this video, please hit the like button, and if you are not yet subscribed, please consider joining the Dr. Data Science team. The first question that we are going to answer here is why should we use spectral clustering? And we answer this question by creating a synthetic or simulated dataset. We import NumPy as NP, we import Matplotlib for visualization purposes, and we're going to also import K-means clustering, which is one of the most widely used clustering techniques. Here we use also make blobs to create the synthetic data. And here you can see that we have both the input features, which we have here called X. So this has 1500 rows and 2 columns. We have a 2-dimensional data set here. And although here we have this Y, which gives us the labels or target values for each data point, we are not going to use them because we are working with an unsupervised learning problem, meaning that we want to find groups or clusters of similar instances in the data. To make this problem a little bit more complicated, we are going to create an isotropically distributed data by transforming the data that we created, which we called X. So after we create this transformation matrix, which is a 2x2 matrix, we're going to multiply this by the data matrix X. And now we have this X aniso, which means that this has an isotropic distribution. And we can see here on the top figure that this data set consists of 3 clusters. And obviously we have this anisotropic distribution here. And if we apply K-means clustering with 3 clusters as the number of input clusters that we give to this algorithm, and we use fit_predict to fit the K-means clustering model and predict the labels for the input data set, we use the plt.scatter to have a scatter plot. And the reason that now here is color coded because we have specified the C argument to be the predicted labels y_pred. And we can see that here we are not successful to correctly identify these 3 groups in the data. And the reason is that the K-means clustering algorithm finds 3 cluster representatives or centroids. And then we have these types of like spherical distributions around each centroid that tells us each data point belongs to which centroid. And because this data set is not linearly separable, therefore K-means clustering fails to provide reasonable clustering of the data. And therefore we are looking now for a more sophisticated clustering algorithm that is able to correctly identify these clusters. So this is the motivation why we want to learn about spectral clustering. Spectral clustering consists of 3 main steps. The first step is to form what is called as a similarity graph. And the similarity graph means that here each data point in our data set is going to be a node or a vertex in a graph. And now we are going to have this adjacency matrix, which we call this K. And this matrix contains information about the similarity or the weight of the connection between each 2 nodes. And because in this problem we assume that we have n data points, x1 to xn, these are the n rows of the matrix X or X aniso that we had in the previous slide. So now we will have this n by n matrix, which has n squared elements, all the pairwise similarities that we have. And now if you look at the row number I and column number j, which we show this by k of xi and xj, So this is the similarity or the weight of the connection, and this is obviously inversely proportional to the distance between the two data points. And one common way to define this similarity is using the exponential function, what we also see in calculus as e, like when you say e to the power of 1 or 2, so the exponential function. And here, the way that we define this is that the similarity is defined as exponential of negative gamma. In this, gamma is the hyperparameter, means that we have to set this value before starting the clustering process. And then we multiply this by the distance squared. And you can see here that because we have the exponential of a negative number, when the distance is equal to 0, exponential of 0 is equal to 1. So that's the maximum similarity. And then as the distance between the two nodes or the two data points increases, the similarity decreases. So we have this inversely proportional relationship. And the decay rate, or how fast we get close to 0 in terms of the similarity value, depends on the hyperparameter gamma that we have to do hyperparameter tuning. So the first step is to form this adjacency matrix, which is K. Now you may wonder how we can do this efficiently in Python, and we can use the SciPy package. So from SciPy.spatial, we import distance, which has a lot of useful functions to find pairwise distances. And this rbf_param is the parameter for that exponential function. That exponential function is also called as radial basis function sometimes, and that's why I call here rbf_param. And here I just chose some value that I know that it's going to work, but in general, if you have a new data set that you're going to work with, you have to tune this hyperparameter. So the first thing that we are going to do is to find this adjacency matrix K, which is the exponential of negative gamma times all these pairwise distances. And this distance that we imported from SciPy will compute all the pairwise distances between the rows of that matrix X aniso, which, if you remember, that's the anisotropic version of the original data set that we created. That was the part that was challenging for K-means clustering. The other thing that we have to do after forming this adjacency matrix is to find the sums of all the n rows of this matrix. So you add all the elements in the first row, and we call this value d1, and up to dn. So this, instead of d2, should be dn. This is just a small mistake here. And then we create this diagonal matrix, which has all the elements d1 to dn on the main diagonal, and the rest of elements are zeros. And we use these to normalize the adjacency matrix that we have. So now we have this matrix M, which is d to the power of negative 1/2 kernel matrix, or the adjacency matrix K times d minus half. So obviously this matrix M is still a symmetric matrix, because if I find the transpose of the matrix M is still equal to M. How can we do this very efficiently in Python? We can find the sum of each row using k.sum access equals 1. So if you set access equals to 0, you're going to find the sum of elements in each column. But when you set access equals to 1, you're going to find the sum of elements in each row. And then we have to also find this d to the power of negative half, which the way you can do this, because this matrix, this d here that we found in Python is a 1D array. So you can just divide this 1 by d. So this gives us d minus 1. And then when you take the square root, that would be d to the power of negative half. And that's the challenging part here, because the matrix K is a two-dimensional array, but D here is still a one-dimensional array. So one way is to convert this to a two-dimensional array and do the matrix multiplication. However, that can be very computationally expensive if the number of samples is large. This n that we used in the previous slide. So in order to do this very efficiently, you can use this trick using np.multiply from numpy, that you're gonna create this two-dimensional version of d using this np.new access, and np.multiply, because it does element-wise multiplication, this will multiply the diagonal elements of d minus half by the kernel matrix K. To understand this step better, I created a very simple experiment. So here I created a matrix A, which has 3 rows and 3 columns. And you can see here, so the first row of A is 1, 2, 3, the second one 4, 5, 6, and the third row of A is 3, 4, and 5. And my goal is that to multiply each element in each row by the corresponding value from the one-dimensional array D. So D has only 3 elements, has 1, 2, and 3. So I want to multiply the first row of A by 1, and the second one by 2, and the third one by 3. In order to do this efficiently, you can create a two-dimensional version of D using this dnp.new access. And what this does is that it's gonna like broadcast 1 to the first row. So now we got 1, 2, 3. And then the second element of D, which is 2, is gonna be broadcasted to the second row of A. So that's where we get 8, 10, 12. And similarly for the last row, we are gonna get 3 multiplied by each element of the third row. So we get 9, 12, and 15. And here also I have printed this dnp.new access to show you that now this is a two-dimensional array. I have a video before on how to distinguish between one or two-dimensional arrays in NumPy. I definitely recommend you to look at that video if this is something that you're not familiar with. But in general, when you look at this NumPy array D here, the one that we had on the top, you can see that we only have one square bracket, a pair of square brackets, and then for A, we have one pair of square brackets, and inside that we have these square bracket 1, 2, 3, 4, 5, 6, 3, 4, 5. So this is A is a two-dimensional array and D is a one-dimensional array. And just going back to the previous slide, when you want to do this multiplication, you can use this trick that we have here using np.multiply, and you will find the matrix M, which you can think of this as a normalized adjacency matrix. So you find the adjacency matrix K, you plug that into this equation using the sums of rows of the matrix K, and you find the matrix M. And also here I want to emphasize the connection between the normalized adjacency matrix that I showed you, M, and something that is very common in the context of a spectral clustering, which is known as the normalized Laplacian matrix. So if you read some textbooks on spectral clustering, you definitely see this matrix L, which is called the normalized Laplacian matrix, which is the identity matrix minus this normalized matrix M that we just talked about it. So here you see the connection between the normalized Laplacian matrix and M. So the difference is that M can be written as identity matrix minus the Laplacian matrix. And the main difference is something that you see in the next slide in terms of the difference between this second step of spectral clustering. So after you find the matrix M, you're going to use eigenvalue decomposition, which is a matrix factorization that gives you these orthogonal matrix U, which has these columns U1 to Un. So these are the eigenvectors. And then you get this diagonal matrix sigma, which has these diagonal elements sigma 1 to sigma n. And these singular values are sorted in decreasing order. So when you're using the matrix M, you're going to keep eigenvectors corresponding to the largest eigenvalues of the matrix M. And it is common to keep exactly the same number of eigenvectors as the number of clusters that you want to find. So in this problem, we had 3 clusters. So that's what I'm going to keep all the rows of U. And then for the columns, that's when I'm doing the indexing. I want to keep the first, second, and third columns. So that will be 0, 1, and 2. And remember that whenever we're using indexing, the first one is always including and the last one is excluding. So this means that 0 is included and 3 is not included. But still we have index 0, 1, and 2. So these are the first 3 columns of U. And we can do this eigenvalue decomposition using SciPy. So from SciPy, we import linalg, stands for linear algebra. And we use linalg.svd. And we're going to find this U and sigma. And because we want to just look at the first k columns, where k here is the desired number of clusters, we are going to do this indexing to find a subset of U. So recall that now this matrix U has n rows and 3 columns. So it's an n by 3 matrix. So the other difference here is that if you used the Laplacian matrix, the matrix L that we just talked about in the previous slide, now you had to pick eigenvectors corresponding to k smallest eigenvalues of the Laplacian matrix. So that's the difference here. And because it's usually easier to pick the largest eigenvectors corresponding to the largest eigenvalues, that's why I prefer to use the matrix M. So in this case, we just look at the eigenvalues that they are the largest. And the last step of spectral clustering is to apply the K-means clustering algorithm, which ironically we said that that doesn't work here, but the difference here is that we are applying the K-means clustering algorithm to the n rows of that matrix U that we just found in the previous slide. So here we have again the sort of like the eigenvalue decomposition that we just talked about it. And then what you're going to do is that you're going to apply the K-means clustering to that subset of U that we found, which is n by k, where n is the number of samples and k is the number of clusters. It is also common to normalize each row of that subset that we found. So for that, you can always use the scikit-learn that preprocessing, which has this built-in function normalized that will do that for you. So that's why we have this normalized U subset. So this will make sure that each row of the matrix U is normalized to be 1. And now by applying K-means clustering to these n rows of the matrix U, we get these predicted labels that are as a result of a spectral clustering. And similar to before, we're going to visualize the input data, which is this X aniso, which is the anisotropic distribution of data that we created. And also we're gonna now plot in the second subplot, we're gonna plot the data with these labels that are color coded. And as we can see here, we are able to correctly identify the 3 clusters that we had in the original data. And again, the main difference here is that we apply the K-means clustering to the top eigenvectors of the matrix M, which was the normalized adjacency matrix, instead of applying K-means in the input space. And that's sort of like the big idea behind spectral clustering, that what we are going to do is that we get some input data, we are going to find a transformation of data, and after we find that transformation through eigenvalue decomposition, now we can apply K-means clustering algorithm, which is good at finding linearly separable clusters. And one more thing that I want to emphasize here is that the performance of spectral clustering heavily relies on proper values of that parameter gamma that we had in that exponential function. So you always have to tune that parameter to be able to find reasonable clustering results, and that's something that you can use like grid search CV or other built-in function in scikit-learn. Thanks for watching, and I hope you found this video useful.